In this video, we're going to look at chemical changes and how we can identify the likely entropy changes involved. For changes like going from a liquid to a gas, so boiling your water, this is always going to have a positive change in entropy. Gas molecules are just much more free in how they can move, how fast they can go, their motions and everything, than a liquid is. Liquids are still bound to be held together by the other liquid molecules, and while they can roll over each other, they're not nearly as free in their motion and ability to distribute their energy and position as a gas is. So we always expect an increase in entropy as we go from a liquid to a gas. Similarly, as you go from a solid to a liquid, you also expect a change in entropy to be positive. However, less than from liquid to gas. A solid is rigidly locked in place. It has all of its molecules more or less locked in place, and it at best turns into a slightly rolly liquid where particles can kind of drift over each other. But going from a liquid to a gas where everything is super spread out will always be a much greater increase in entropy than going from a solid to a liquid. Additionally, as our temperature rises, we expect that our entropy will also rise. The more thermal energy you have to distribute among your particles, the more possible states that they have to distribute that energy into. And so as your temperature increases, your entropy should also increase. Solutions are a little less clear. Some salts, like sodium chloride, will indeed dissolve in the water and become sodium aqueous and chloride aqueous. And as they spread out within a container, so original solid block, but they start to spread out over time as your solid dissolves. That increase in distribution, being spread throughout the whole container instead of localized in one area, is far more entropic than being the solid. The solution definitely favors dissolving sodium chloride. However, to do it, your water molecules, which could be kind of in any direction and freely moving around as much as they wanted, passing through each other, these had to line up and become orderly to solvate the ion. And they have to lock into place to do it. The waters actually become less distributed. They have less options for their motion and their angles and their rotation. So while there is an increase in entropy for the salt, there's a decrease in entropy for the water. Now, as long as dissolving the salt nets you a greater change, this is generally going to be favorable and dissolve. But there are plenty of salts that really do not dissolve nicely. Think lead iodide. Breaking that 2+ ion and the iodines apart is much more difficult. Lead iodide is not readily soluble in water despite being nicely ionic. Not every ion is going to dissolve nicely in water. It may require too many waters to arrange to solvate it, such that the entropy lost from water is greater than the entropy gained from solvating the ions, in which case this largely becomes disfavored. On top of it, gases in solution, like O2 gas bouncing into a water, becoming O2 aqueous, getting those gas molecules stuck among the water. The gas is small, lightweight, weak polar attractions to other things. It wants to be bouncing around at its own at that temperature. To be trapped in place by a bunch of water molecules as it flows around inside the water gives it much less freedom of motion. A dissolved gas is always at negative entropy versus free gas. Now, particles slam in the surface all the time. Some of them have enough energy to get trapped. Waves fold over and trap air bubbles that pull it down. And so there's always some gas in the water. But that gas is not particularly favored. It takes the wave motions and the heat energy of the gas bouncing around, slamming into the water surface to get those molecules to go into it. As a result, there's actually significantly lower concentration of oxygen gas in the ocean than in the atmosphere. Fish have far less oxygen to work with than air breathers do. On top of this, different molecules of similar construction, think HCl and HI, can have wildly different entropies. Heavier elements tend to form molecules with greater entropy. The reason for this is that heavier elements actually have more possible microstates. The more mass you have, the more available amounts of energy and speed of motion and rotations that you can have as a result. And so HCl versus HI, there's just a greater variety of possible combinations and distributions of energy among a bunch of HIs than there is among a bunch of HCl's. And for chemical situations, that's really the core of it. Motional energy. Sometimes we think of it as kinetic energy, but it's possible for these to not be moving within the distribution. So the motional energy is just the distribution of all the varieties of motion that our particles can have. Vibrations, rotations, and translations. Molecules, if you think of, say, water, well, those hydrogens pull in and push out. They stretch in and out. They vibrate. Technically, the OH bond vibrates. And the second one does it as well. It can stretch out and pull in. As those electrons draw the nuclei to the center, they can start moving in, they get a little velocity, and then they start getting too close. The nuclei start to repel their positives. They start to slow down, but now they're too close and they start to push away. And they'll bounce back and forth around an ideal bond length. Well, that can be faster or slower. Depending on the amount of energy, you can vibrate at faster speeds or slower speeds. And so there are multiple vibrations that you can be at. Additionally, you can also be asymmetric. One can go in while one goes out, and then they'll go back the other way. Or they can be symmetric. They can both be going out at the same time, and then both be going in at the same time. Additionally, your hydrogens can kind of bend towards each other or away, effectively changing the bond angle between them. As they get too close, the Vesper repulsion pushes them away. As they get too far out, they'll get near the lone pairs. They'll push back. And so these will vibrate by bending around the oxygen. So there's multiple modes of vibration. Additionally, the whole molecule can simply rotate. You can rotate around this axis. You could rotate right around the oxygen, or you could rotate around this axis. The different axes of rotation can be at different speeds. There's different quantized levels of rotation and vibration, and so there's a variety of ways that you can distribute energy into this molecule. Each axis can have a different amount of energy, and the next molecule could have a different distribution of energy among those axes. You can be vibrating asymmetric on one and symmetric on the other. You can be doing it at a faster speed on one than the other. And additionally, translation is what we normally think of for something just moving. It can be moving slow, it can be moving fast, it can be moving really fast. There are a lot of ways to distribute energy within molecular shapes. And so when we think about the entropy of a chemical system, how the energy is distributed between its motional energy forms is a key component of our entropy discussion. It helps us understand why different molecules, even if they're about the same mass, might have wildly different amounts of entropy. If there's more atoms and more vibrations available, then a molecule can have significantly increased entropy versus another one.